Hey everyone. Today, we're going to crack a classic computer science puzzle. And we're going to do it with a solution that, honestly, it feels like a magic trick. We're going to find the longest path in any tree network. And all it takes is 2 simple steps.
So think about it for a second. Imagine any kind of network, roads, servers, maybe even social connections. If you wanted to find the 2 points that are the absolute farthest apart, how would you even start? Well, that's the core question we're answering today, but for a specific kind of network structure called a tree. So, in the world of computer science, this longest journey has a name. It's called the tree diameter. It is, quite simply, the longest possible path you can find between any 2 nodes. For a simple little tree like this one, you can see the diameter is a path between these 2 nodes way out on the edges. The real question is, how do we find it when the tree is huge and we can't just eyeball it?
Okay, so the solution is this wonderfully clever algorithm that basically just involves running the same search process twice. It's so simple that it almost feels like it shouldn't work, but it's guaranteed to give you the right answer every single time. So let's check out the recipe.
Here it is. It's just 2 steps. First, you pick any node you want in the tree. Seriously, it does not matter which one. And you find the single node that's the farthest away from it. We'll call that node X. Then, for step 2, you start from X and you do the exact same thing again. Find the farthest node from it, and the length of that second path, that's your diameter. I know, it sounds way too simple to be true, right? Let's just walk through an example and you'll see it in action. So, here we go with our example tree. Let's start with step 1. And remember, the goal here isn't to find the diameter itself just yet. Nope, we're just trying to find one of its 2 endpoints.
And like the recipe says, our starting point can be completely random. So let's just go with node 1. From here, we're going to kick off what's known as a depth-first search, or DFS. All that really means is we're going to explore as far down one single path as we possibly can before we backtrack and try another.
Now, as our search does its thing, we're going to keep an eye on a few key variables. First is depth. That's just our current distance from where we started. Then there's best. That stands for best, and it stores the longest distance we've found so far. And finally, we have far, which remembers which node actually gave us that best distance.
This one line of code, this is the heart of the whole operation. As the algorithm travels through the tree, every single time it lands on a new node, it asks a really simple question. Hey, is the distance to get here greater than the best distance I've seen so far? And if the answer is yes, it just updates its memory. It says, okay, this is the new farthest node. The search is just going to keep doing that. Travel down a path, backtrack, explore another, constantly asking that one simple question. Is this one farther?
And there we have it. After checking out the entire tree, our algorithm figures out that the node farthest from our starting point, node 1, is actually node 5, which is a distance of 3 away. So node 5 becomes our X. We found an endpoint. All right, now for part 2 of the trick, we're going to do that exact same search all over again. But this time, our starting point is special. We're going to start from the node we just found, node 5. So we just hit the reset button on our BST and far variables and kick off that second DFS. The process is a total carbon copy of the first one, but our starting line is now X, which for us is node 5. This second search is the one that's going to give us the final answer.
You can see our variables right here, all reset and ready for round 2. BST is back to -1, and our starting point is officially node 5. So, off we go again. The search expands out from this new starting point, exploring every single path, keeping track of the depth, and just like before, it's constantly updating that BST value whenever it stumbles upon a node that's even farther away.
And we are right back to this simple little comparison. Our algorithm is doing the exact same work, but here's the cool part. Because we started from that special node we found, the final value it gets for BST isn't going to be just some distance. It's going to be the diameter of the entire tree. After searching the whole tree from node 5, the final value that BST settles on is 4. And that's it. That's our answer. The diameter of this tree, the longest possible path between any 2 nodes, is 4. So we've seen that it works. It's fast, it's simple, it gave us the right answer. But the real magic, the really cool part, is understanding why this is guaranteed to work every single time, no matter what kind of tree you throw at it. I mean, this is the question, right? This is what separates a neat little party trick from a rock-solid algorithm. Why can we be so sure that just picking some random starting point is going to lead us to the right answer in the end? The entire proof, the whole secret,
hinges on this one really powerful idea. It turns out that no matter where you start in a tree, the node that is the absolute farthest away from that starting point is guaranteed to be one of the two endpoints of a true diameter. Let's break down why that is. We can pretty much prove this by just thinking about two possibilities. Case 1, we get lucky, and our random starting node just happens to already be one of the endpoints of the diameter. In case 2, our starting node is any other node, somewhere inside the tree. Okay, so the first case is super straightforward. If we just happen to start at one end of the true longest path, well then by definition, the farthest node from us has to be the other end, right? So our first search finds that other endpoint, and then the second search just correctly measures the distance between them. Easy peasy. But what if we start somewhere in the middle? Well, just picture the true diameter, that longest path, sitting in the tree. Now imagine a path starting from our random node. For that path to be the farthest possible path from our start point, it has to stretch out as long as it can. And at some point, that path is gonna have to cross the true diameter. To make itself as long as possible, it has no choice but to follow that diameter all the way to one of its endpoints. Taking any other turn would make the path shorter. So no matter what, the farthest node from any starting point will always be a true endpoint of a diameter. And that's really the whole secret. That first DFS isn't just a lucky guess. It is a mathematically guaranteed way to find one of the two nodes that define the tree's longest path. Once you've got one of those endpoints, the second DFS is just a simple matter of measuring how far it is to the other one. So this double DFS trick is an absolute powerhouse for tree structures. But what happens if our network isn't a tree? What if it has loops or cycles? Well, then this method doesn't work, and finding the diameter suddenly becomes a much harder problem to solve. That's a question to leave you with, and maybe, just maybe, something for another explainer another day. Thanks for watching.